You've transcribed. You can complement DNA bases with RNA bases. Ooh, thiamine, you are looking lovely today. But can you actually figure out the exact amino acids that RNA calls for? Ha! You'll be able to now. Let's do protein synthesis, the real nitty-gritty. It's me, Moser. And after you've watched this video, you should be able to transcribe DNA to mRNA and then use a codon chart to translate mRNA codons into amino acids. You should be able to demonstrate a mutation that doesn't change any amino acids and explain how that could possibly happen. You should be able to demonstrate a mutation that does change a single amino acid and explain how that's possible, and demonstrate a mutation that changes multiple amino acids and show how that works. Now, you should already know, DNA versus RNA, all your bases, transcription, translation, and the 3 types of point mutations. You're also going to need a codon chart. So why don't you go ahead and grab that. You know that all living things, both prokaryotes and eukaryotes, construct proteins. You also know that the instructions for those proteins are contained in DNA, copied over to mRNA, and read by ribosomes, 3 letters at a time. Each of these 3-letter words or codons specifies an amino acid. You got that. Now, if we know the DNA sequence, we can actually build the protein that it provides instructions for. So let's start with the DNA sequence and transcribe the correct codon sequence to complement it. The DNA sequence shown here, TAC, GTG, CAC, TGA, CCT, GAG, gives us the first 7 amino acids in the protein hemoglobin, which is used by you and me and blue whales and coyotes and, all mammals to transport oxygen in the blood. It's easier to work with this sequence if we arrange it into the triplets or the 3 base chunks in DNA in this neat little frame. Okay, go ahead and complete the mRNA codons. You should have, for your mRNA codons, AUG for TAC, CAC, GUG, you know these. GAC, ACU, GGA, CUC, yeah, you got it. Now, the tool that we're going to use to determine which amino acids are called for by each codon is called a codon chart. There are 2 basic styles of codon chart, the grid and the circular chart. They're both shown on your fill-in notes in miniature, and here's an example in real life of each of them. You're going to have to learn to use both of them. If you haven't already done so, grab a full-page 2-sided codon chart handout to go with this. Let's go from that mRNA sequence you transcribed above. The first codon is AUG. Let's start with the grid chart. The first letter of the codon is A. So we start in the 3rd row down, right there. For the second letter, we look at the headers on the columns, and the second letter is U. So we're going to look in the second column. We now have this narrowed down to this box. Now, the final letter of the codon is G, so we look at the bottom row in that box. AUG codes for methionine, which is the start codon. So let's find the next few together using the grid codon chart. So for CAC, we'll start in the 2nd row down with C. Look at the 3rd column for A. And finally, we look at CAC. This codes for histidine, abbreviated H-I-S. GUG gives us fourth row, first column, and it looks like no matter what our third codon is, our amino acid is valine. Okay, do you feel like you're pretty comfortable using the grid codon chart? Now let's practice working with the circular chart. I find the circular chart easier, but it's all a matter of personal preference. For the codon GAC, we're going to start in the quadrant of the inner circle marked G. We're going to go out through the letter A and then out through C, right there. And that tells us that the codon for GAC is aspartic acid. We'll finish the rest of these using the codon chart. I've got A, C, U, threonine, GGA, which is glycine, and finally in this little short sequence, C, U, C, which is leucine. Okay. Doesn't seem that hard. You'll get more practice, don't worry. This really doesn't seem hard. But what happens if something goes wrong in the process of DNA replication and the DNA triplets aren't as they should be? Remember your mutations to a single base, your point mutations? So let's look at the effect of the three kinds of point mutations in DNA on the amino acid sequence. Here's the sequence we've been using with one difference in the DNA. What is it? Well, we've got a substitution mutation at the sixth base, which changes the second triplet. GTG became GTA. Will that change the mRNA codon? Yes. Will that change the amino acid sequence? Well, there's only one way to find out. CAU gives us, well, wait a minute, gives us histidine. That's the same amino acid we had before. What? The sequence of the amino acids is the same. And we can go through and check all the rest. Nothing changed. The amino acid sequence is the same, despite there being a mutation. How can this be? Well, look at either codon chart. There are 64 possible combinations of bases forming codons, but there are only 20 amino acids. And several amino acids, like leucine and serine, are coded for by multiple codons. A substitution mutation like this one has a pretty good chance of not changing the amino acids. Could a point mutation ever shorten a polypeptide chain? Look at the DNA sequence below. There's a substitution mutation in the sixth triplet. CCT became ACT. One base, no biggie, right? Unfortunately, when we check the DNA triplet ACT, we find that it's transcribed to the mRNA codon UGA. That, my friends, is a stop codon. This polypeptide chain just got cut short. Well, what about the other two types of point mutations we talked about earlier? Insertion and deletion. Let's go back to our original DNA sequence. What if during replication an extra base was inserted, like this one? There's an extra G. It's only one base, but because of that insertion, look at how all the other bases shift their triplets. This changes all the codons from that point, and that single change from that one point changes every single amino acid from the point of the insertion onward. Ooh. What about a deletion? Here we go. Will a deletion change things as much? Here's our original sequence, and here the fourth base has been deleted. Now, when we put this into our neat little frames and we run the mRNA codons, If you compare this to the sequence of mRNA codons we had above, you see that once again, every codon has changed. Because this changes every triplet and every codon after the deletion. In addition, of course, this changes every amino acid after that point. Yikes! All from the insertion or deletion of a single base? Yeah. This is because insertion and deletion mutations often cause what are known as frame shift mutations, shifting all the bases up or down one position and changing the codons that get read by the ribosome. This is like when that lovely frame you bought for your family picture isn't quite lined up anymore. It seriously changes the picture, and that little boy should be very irritated. Frame shift mutations often cause big changes to the finished protein. Think you can build polypeptide chains on your own? I bet you can. Go practice.